Hello everyone, you're welcome to our channel once again. Today we shall be discussing on how to use a Buckingham pi theorem. Once again, how to use a Buckingham pi theorem. Now let's read through the question we have. The question says, use Buckingham pi theorem to determine the dimension groups that are correlated with the vortex shedding problem. Use D, which is diameter, V, which is velocity of stream, and rho, which is the density, as the repeating variables. Once again, use the Buckingham pi theorem to determine the dimensionless group that are correlated with this vortex shedding problem. Use D, diameter, V, the velocity, and the rho, which is density, as the repeating variable. Now, how do we use Buckingham pi theorem? In the first instance, we need to pull out the fundamental dimension. From here, we have three fundamental dimensions, which are what? The D, diameter, the V, the velocity, and the rho, density. Also, we have three repeating variables, just like as we were given, two repeating variables. Also, we have two dimensionless group. Now, looking at the question in which we are asked that there's a vortex shedding, just like the diagram represented here. That is, there's an oscillation and turbulence of the flow after the flow of the stream passed through the cylinder. So these are the representation of the oscillation of the stream, which is called vortex shedding. Now, by using Buckingham pi theorem, first of all, we need to pull out the parameters, which is the diameter, the velocity of the vortex, and the density of the vortex. Now, by using Buckingham pi theorem, we assume that the first three repeating variable has the alpha and the beta and the gamma power input, just like it is written here, while the non-repeating, which is F, the frequency, is left out of the repeating. So the F stands on its own without the power. So therefore, by translating our characteristic property here, which is the density, to the fundamental dimension, we have M over L3. By translating V, we have L over T. By translating D, we have L. By translating F, F stands on its own. So therefore, the variable power carries the particular number of the property inside the bracket. So therefore, the alpha carry -3 because it's on denominator. So therefore, if it is M, it carries 1 because it's on the numerator. So therefore, our M equals alpha, which is 0. Also, the L equals -3 alpha plus beta plus gamma, which equals 0. The same thing with T, which is negative beta minus 1 equals 0. So therefore, our beta calculated equals -1, and our alpha equals 0, and our gamma equals 1 calculated. So this is the application of Buckingham pi theorem. That is, all our dimension groups or all our variables carry different multiple power are translated to its equation here. So therefore, our beta equals 1, our alpha equals 0, and our gamma equals 1. Now, by slotting all these power variables into the former inputs here, we have this particular equation which gives us Stroher number, that is Stroher number of a fluid, which is our Buckingham pi equation, which is df, that is diameter, multiplied by the frequency over velocity, which gives us Stroher number. Now, also, by using this particular equation with the 3 repeating variable, likewise the first one we did, it gave us this particular equation, and from there, by equating all our multiple power, which we have here and here and here, it gives us this particular equation, which is dynamic viscosity over density times the velocity times the diameter of the cylinder. So that gives us the Reynolds number calculated. Thank you very much for listening.